So this is the beginning of section 16.6, talking about integrals for mass calculations. And we are specifically going to look at the review of section 8.3 from Jimmy Stewart Calculus, talking about mass and the centroid. So let's begin with the review. So a mass is a body of matter with no definite shape, and we usually use the lowercase letter m to denote mass. Density is the degree of compactness of a substance, and we use the Greek letter rho to denote it. Notice that this rho refers to density. In the previous section, we used the same letter rho to refer to the distance a point is from the origin in spherical coordinates. Same letter, different interpretation, context is everything. Thirdly, the center of mass, also called the centroid, is the point at which any particular object or mass that we're working with, in this particular definition, thin plate, balances. So it's kind of the balance point of what you're looking for. I think about it with like a textbook, like what's the point that you would hold a textbook at where the textbook would balance at a single point. So the law of the lever talks about how the distance from a fulcrum or from a balance point impacts the center of mass. So, for example, the little child that's far from the fulcrum has just as much impact on the balance point as the larger child who's closer to the fulcrum. And we all know this from our time on a seesaw or a teeter-totter, depending upon what you call it. Another interpretation of this is somewhat analogous to a weighted average. So here's the X's would represent the points that we care about. The M's would represent the weights, and then you divide by the sum of the weights. So for example, we got 30% on this, maybe our quizzes are worth 30%, and we got 80% on those, and our tests are worth 50%, and we got 75% on those. And then we divide by the 30% that was on quizzes plus the 50% that was on tests, and that gives us our weighted average. So that's how a weighted grade is calculated. Next thing we need to talk about are moments. So a moment is a turning effect produced by a force acting at a distance on an object. So I think about this as the tendency to rotate. This is talking about the tendency of something to rotate. And in order to find the tendency to rotate, we're always looking at the mass, the amount of stuff there is at any given point, and then also the distance the point is from whatever our 0 point is. And so the overall x bar would be the moment, which would be the sum of the masses times their distance from the origin. That'd be the moment, divided by the sum mass, which would be the sum of the individual masses. The same thing holds true in 2 dimensions. So if we do this in 2 dimensions, then we could have a moment about the y-axis. And if you want to find the moment about the y-axis, would require you knowing the distance from the y-axis. So here we have the distance from the y-axis. And notice the distance from the y-axis is given by that x value. This all gives you the moment about the y-axis, and interestingly enough, you'll notice that the moment about the y-axis is what's used to find x bar. Why is that? Because what matters for the moment about the y-axis is all those x values. Contrast that with the moment about the y-axis. The moment about the y-axis requires us finding the distance from the x-axis. So here are our distances from the x-axis. So all that combines to give us our moment about the x-axis, which gets used to find the y-bar, or the y-coordinate of the centroid, or the center of mass. So it's a little bit counterintuitive. To find x bar, you need the moment about the y-axis, and the reason you need the moment about the y-axis is because the moment about the y-axis tracks all those distances from the y-axis, which are all x values. So far, we have considered exclusively systems where there were kind of like particles, finite number of particles, and so we could add all those things up with just a summation. But what happens if there's an infinite number of particles, e.g. you have some sort of a continuous object? So if you have some sort of continuous object, we're basically going to do the same thing. And so we will consider a flat plate with uniform density rho. The plate is made out of infinitely many particles. It's continuous. To find its center of mass, or centroid, we need to divide the plate into very small rectangles, which are like particle strips, if you will. Find the center of mass, or centroid, of each of those rectangles and add them all together. The center of mass is called the centroid. Note, the centroid of a rectangular plate with uniform density is its center. So we just need to look at the centers of each of these rectangles. To do this, let's find the moment and center mass of the region under the curve f of x from a to b. The ith interval has subinterval has midpoint, which is at this point right here. So it's this point right here. And so here's your xi hat, or xi bar. The center is at xi bar, and then the y coordinate would be at f of xi bar. But notice f of xi bar would be up at the top, so we want 1/2 of that. So the centroid of the rectangle would be at xi bar and 1/2 f of xi bar. The area would be the overall height times the width. So the overall height here would be this height, and the width would be here. And so there's your area, would be of this rectangle. Okay. And of course, then the mass would be whatever that area is times the density. And this would be area density. So the moment about the moment of the region about the y-axis is going to depend upon the distances that so we're looking for the moment about the y-axis. It's going to depend upon our distances from the y-axis. So our distance from the y-axis is right here. And that distance is the xi coordinate. And so right here in that moment about the y-axis, you see all those xi's showing up. And we're going to take we have an infinite number of them, so there's going to be a Riemann sum and a limit. And after we convert that to a definite integral, we have a formula for the moment about the y-axis as rho times the integral from a to b of x, the distance from the y-axis, times f of x dx. If we want to find the moment about the y-axis, we can do the same thing. Not sure if I can get everything on the same picture. So if I want to have the moment about the y-axis, I need the distance from the x-axis, which would be right here. So notice that height, and this would be 1/2 f of xi. So this right here, that's my distance, and then my distance from the x-axis, and then I'm going to multiply it by f of xi hat delta x, and this stuff represents the area. So again, we have the distance from the x-axis times the area. That will give us the moment about the x-axis. And notice this distance is, again, this right here is the y value at that point, at the given point. If we simplify 1/2 f of xi times f of xi delta x, we get the 1/2 f of xi quantity squared delta x, which is where our formula for the moment about the x-axis comes from. It's rho times the integral from a to b of 1/2 f of x quantity squared dx. Since the centroid is at x bar, y bar, which would be my, the moment about the y-axis, divided by the mass, comma, mx, the moment about the x-axis, divided by the mass of the plate is the product of its density and its area. So remember, mass is equal to density times A, and that would be rho times the integral from a to b of f of x dx. The coordinates of the centroid or the region or the center of mass of the plate can be expressed as the following. Notice that the rows all go away, and the reason is because you have the rho out in front of the mass integral, and you have the rho in front of the moment integral, and these two rows cancel each other out. So the actual x, assuming you have uniform density, the rows cancel out, and we end up with this formula that x bar is equal to 1 over the area times the integral from a to b of x f of x dx. The x here representing the distance from the y-axis, and y bar is equal to 1 over a integral from a to b of 1/2 f of x dx, where at least the 1/2 f of x, not the second one, but is telling us something about the distance from the x-axis. If the region lies between two curves, the coordinate of the centroid of the region or the center of mass of the plate is as follows. Notice it's basically the same formula. X bar is equal to 1/2 times the integral. Y bar is equal to 1/2 times the integral of 1/2. And you have this difference of squares. The one cautionary note here is that this is not, for the y bar, this is not the same thing as f minus g quantity squared. So you find basically you find the y bar for the f function, you find the y bar from the g function, and you subtract them. So it's pretty easy to find. Just as an added bonus, you may recall from Calc 2, when you talked about this before, that there's this cool, surprising connection between centroids and volumes of revolution called the theorem of Pappus. So this is a really old theorem, and it says, let a region such as this one, R, be such that it lies entirely on one side of a line L. So maybe your line L is the x-axis. If R is rotated about L, then the volume of the resulting solid is the product of the area of R times the distance d traveled by the centroid of R. So just making that concrete, if we had a centroid of R, maybe the centroid of R is like, I don't know, right at this point, and we could look at the distance that travels around an axis. So maybe something along those lines. So we rotate it around the x-axis. So this distance would be d. Okay. So if R is let R be a plane region that lies entirely on one side of a line L in the plane. If R is rotated about L, then the volume of the resulting solid is the product of the area of R. So in this case, we'd be looking at the area of R, and then we're multiplying by, in this case, it's kind of cool. It'd just be that distance d, which would be, in this case, 2 pi times whatever that radius is, whatever that distance is, the point is, from our x-axis. So it's just kind of a cool connection between a couple of topics. So everything that we did in this film is simply a review of things that were covered in Calculus 2. In Calculus 4, where we're at now, what we're going to do is we're going to look at finding centroids and moments and masses when we have a non-uniform density. So it's actually going to be quite a bit more interesting and more complicated. We no longer have to assume these perfectly uniform laminas, which is pretty cool. But it's been a while since you did center of mass, and so I just wanted to put this review out there and walk you through the work along for those first few pages in case that would be helpful to you. Hope that is good, and may you have a wonderful day as you understand moments and masses. Take care.